Hey, welcome to this next video of ViZDoom. So what we're doing is we are getting the computer to learn to play Doom, which you see here. This is using a wrapper called ViZDoom around Doom, which lets us use Doom for reinforcement learning. So it lets us control Doom from Python. So here we can see Doom being controlled by Python, but it's just doing random actions. We want to create a neural network that's actually going to learn to play Doom. So then to recap where we are right now, here is the script that we have currently. We are instantiating a ViZDoom object, game equal vsd.doom game. We are instantiating a neural network. Here, if you want details about the neural network, you can look at the script or you can look at the previous videos. This is part of a series. Right, then having got the game and the network, we're looping over episodes. So each episode is like one game. Like the player starts with full health, full ammo, starts shooting the monster. We do game.newEpisode for each episode. And then while the game is not finished, we get the state of the game. Each iteration around this loop is a single time step in the game. And we're going to get the screen buffer, which is what you can see on the screen. We take this screen buff, we send it through the model. The model takes what we see and it converts it into action logits, which is a vector of numbers deciding which action we're going to do next. We convert that vector of logits into probabilities. So these action probs represent the probabilities of each action. So the three actions in this game are the agent can go left, it can go right, or it can fire. So there are three actions, three possible actions. Therefore, there are three numbers in the action probs, and each of those numbers represents the probability that we would choose that action. Now, that said, right now, we're not sampling the action according to the probability. We take the action with the highest probability, and we always choose that. We're taking an argmax over those probabilities. So it will always do the same thing, and there's no way we can learn from this. In this video, instead of taking the argmax, instead of always choosing the most probable action, we're going to sample from the actions according to that probability distribution. So if one of these actions has a probability of 10%, 10% of the time we would choose that, even though the most likely action is a different action. And having sampled that action, we can then use reinforce to create a reinforced loss, which we can backprop. This will let the network learn. This means that the network can then learn to play Doom by itself. So let's get started.
Yeah, so let's figure out how to do the sampling. So we're going to go to the pytorch.org doc. So pytorch.org/docs. And then we're going to find the distributions. So distributions, and if we go to distributions, luckily for us, it tells us exactly what to do. It's talking about like reinforcement learning. Reinforce, this is the algorithm we're using. So reinforce does not equal reinforcement learning. Reinforce is an algorithm to do reinforcement learning. It's also called policy gradients. It's not the only way. You'll also hear of like Q-learning and various other things like that. So we're going to use policy gradients. So there's a whole bunch of maths, but basically we don't have to do the maths because we just do this. It does it all for us. So let's first start by sampling our action from the probability distribution rather than argmaxing. So policy network is the model. Probs is the probability distribution. We're going to create a categorical distribution from the probabilities, and then we're going to sample for that. So let's do that. All right, so it's torch.distributions, right? So from torch, import distributions. All right. Oh, I guess we should run this again first, just to check it runs, right? So Python, ViZDoom, part 4. So this is like part 4 before we modify it. And then the version I'm going to save out to GitHub is the modified version. All right, so there we go. So it runs and does random stuff, sort of, and gets negative 200 reward because it's never actually shooting the monster. But if you run enough episodes, eventually it will shoot a monster and get some positive reward. All right. Okay, so yeah, so let's import the distributions. And All right, so we're going to stop doing the argmax. And so we've got the probability distributions. I've got so much dead code here. Should we delete some of this dead code? I'll delete some of it anyway. All right, I guess we can, well, we can leave that. All right, so I guess we can delete that. All right, so basically first we're going to create this thing called M, which is a distributions dot categorical, and we pass in the probabilities. All right, so we simply do categorical on the probabilities, and then we do m.sample gives us the action. So action equal m.sample, and so we can print the action, which hopefully is an integer. I guess we can print the type of action, and we can also print the probabilities, and we'll just run that like that. We have to learn to spell categorical, so there's a C here. All right, so here's the action probabilities. The most probable is this one, so it'll be index 1. But because it's sampling, it actually shows index 0. And it's a torch.tensor. So if we want to turn this into a number that we're going to pass as an index into the actions list, then we need to call .item. All right, so let's run it again. We're going to get a different probability distribution. Here the maximum is index 0, but it's chosen index 2, and now it's an int. Okay, so actually we can simply pass that as input here. So yeah, right. So let's run that. So before, remember that it was sort of always doing the same thing, but now that it's sampling, sometimes it moves left, sometimes it moves right, sometimes it fires. So it's exploring the environment a bit more. It's not learning yet, but it's at least like exploring. So there we go. All right, so let's, I guess we can leave that in. Right, so we have now got it sampling, so good. Right, the next thing is we need to make it learn. Right, so how to make it learn? So I guess there's a couple of possible ways to do this. One is reward per step. I'm not sure if that would work. I think it might work, but it would be really, really slow to learn. I don't even know if it would work. And then the other word would be reward per episode. So, well, anyway, so let's first think about it. So it's making a bunch of moves. Like let's say it starts off and the alien is here. This is the alien, and then so this is like the scenario viewed from above, right? Alien is over here. Player P is here. And basically what needs to happen is the player needs to move left, 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 and then fire, right? So ideally it should do left, 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 and then fire, okay? I guess I can write that out. All right, so this should be the moves it makes. Time step 1, it should do left. Time step 0, it should do left. Time step 1, it should go left. Time step 2, it should go left. Time step 3, it should go fire. That's like the ideal moves. Now let's think about what rewards it's going to get at each step. Well, actually, let's print the rewards, right? So we're going to print the rewards, and let's get rid of this so that it's less spammy. All right, so let's run that and see how that looks. All right, so basically each step is getting a reward of -1. I'm not sure what the -6 is. I guess the aliens shot us or something. And sometimes we should get a positive reward. I assume that if we actually succeed in shooting the alien, we're going to get a positive reward. All right, so there it shot the alien, right? We saw the alien die. And see, look, here we get a reward of 100. All right, so we get -1 when we don't, like nothing happens, we just pass time, and we get 100, or the model gets 100 when it shoots the alien. Right, so going back to here, the reward is, so here we get -1, -1, -1, 100. All right, now we're going to use this reward to train our network. So we're gonna tell the network, look, hey, you got a -1, you should do what you just did less. Hey, you got a -1, you should do what you just did less. Oh, you got 100, so you should do that a lot more. Well, let's think about what would happen if we trade it per step. So the player makes a single move, goes left, and we say, "Oh, -1, don't do that anymore." What is it going to do? It's going to start shooting or going right, right? I mean, it's like teaching it to do the wrong thing, not to do the right thing, right? And then eventually, when it fires and kills the alien, it's going to get like 100. So it's like, oh, okay, I should do that a lot. So after a bit, what's going to happen? All it's going to do is shoot, right? So that's not going to be really useful. So what we really need is, I feel, is to do. So this is like reward per step, right? What we really need, I feel, is to calculate the total reward for an entire episode, which here is 97, and then we're going to give that reward to each of the steps that was done during that episode. So we're only going to give the reward to the model at the end of the episode. So if it manages to shoot the episode, everything that it did for that entire episode, we're going to give it a nice positive reward. And if it gets to the end and, it didn't actually kill the alien, right? So it's just -1 every time. Like the original reward, right? The reward the game gives it. Then the actual we're going to give it is we're going to give it -4 for each step. So it's going to learn, all right, what I did this episode, that was bad. We're not going to do that anymore, right? So we're going to take the total reward for an entire episode, and that's what how we're going to do the reward.
All right, now looking at the PyTorch code, let's take this code here, paste it into here, get rid of this comment. Right, now this, right, so the state is the thing that comes from the environment. This is the model. So for us, this would be model. This would be something like screen buff t, something like that. And then this is like action probs, right? Then from the action probs, we pass that into category, we get this M object. Now the M object lets us sample from that distribution, right? So let's say the action probs is, let's say 0.5, 0.2, 0.3. And then when we do sample, 50% of the time, the action will be 0, 20% of the time when we sample, we will get a 1, and 30% of the time when we sample, we will get a 2. It's like rolling a 3-sided dice, but one side is more likely than another. All right, so the M lets us sample, and the M is also going to let us do the loss in a set. Right, now this, let's put this down here a set. All right, so we're iterating over episodes. Let's pretend we've imported editors, which lets us do that. Right, and then within each episode, we're iterating over step. Right now, we're not exactly doing like this, but like this just makes it easier to read, I think. Right, then this is happening each step. Like, so here we're doing something like game.new episode or something like that, right? All right, and then, well, you know what we're doing, like, well, not game dot it's finished or something like that, right? I don't remember exactly, but something like that, right? We're getting the screen buff from. All right, so we're getting the screen buff from the game. Like it's something like game dot, I don't know, get screen buff or something like that. I don't remember exactly, but approximately getting like that. We're passing it into the model. This is like pseudocode, right? Passing them into the model, we're getting the action prods. Like there's a softmax involved, which I'm not writing here, right? Or I guess we could do like softmax dim equal -1. I guess we could do like this. All right, so we get the screen buffer from the game. We pass the screen buffer through the model, pass that through the softmax to get action probs, pass the action probs into the categorical. We get this categorical object. We can then sample from that to get the action. Right, then we're not using this. We use this r equal game dot make action, right? So we have r equal game dot action. So here it's reward. So we've got reward equal game dot action, actions, action. Okay, now we get this reward every step. So we'll call this step reward. But when we do this loss, we need the episode reward here, right? And this will be within each episode. This will be within the iteration of episode. We're going to calculate the loss at the end of the episode, and then we're going to back-propagate that, right? So to get this episode reward, we will go here, and when we will add the step reward to that each time. All right. So we have the episode reward. But what about this? Right. So we've got a couple of options. One is we could store all these M's and we could store the actions. But you know what? We don't need to do that. Right. We can simply store this. Right. So we can have like M log prob or something like that. And then here we can just do M log prob L dot append. And then we're going to do, we've got M here, right? So we can do M dot log prob action, right? And then for this loss, so then we can just do like for M log prob in M log prob L, and then we're just going to multiply that by the reward. So that gets us the loss, and then we'll have to like sum this up somehow. So some sort of summing thing here, right? All right, so this is how we would do the reinforced loss. So basically, each step, we have the action probs, we create a categorical, we sample from that to get the action. We can pass the action into the environment to get the step reward, and then we add each step reward to the episode reward. The episode reward is going to be used when we calculate the loss at the end of the episode. Now, when we calculate the loss at the end of the episode, we need this m.logprob action. Oh, this should be minus, right? We need this m.logprob action. But the thing is, we have everything to calculate this each step. So rather than calculating this at the end, we simply calculate this each step, m.logprob action, append that to a list, and then we can use that to calculate the reward at the end of the episode. All right, so that's what we're going to do. And so now we're actually going to do that in our actual code.
All right, so going back to our code, so we're going to keep this for each episode. We're going to have like action log probs or something, and we make it a list. We need the action and we need M. So here we've got the action. So here we've got m.log prob action. Action should probably be a tensor. So let's do the action equal action.item after this. All right. And so this is like our log prob. And we can print that. And then we're going to add that to action log probs.append log prob. Yeah, so let's see how the log prob looks. Log prob. All right, so log prob is a tensor. Yeah, it's got a grad event, so you can backprop, etc. Yeah, so I mean the thing is with reinforcement learning, you can't actually backpropagate through the categorical. But if we keep these m.logprob actions, then we can use the reinforce, which doesn't require backpropagating through this. It's sort of a way of doing backprop in the context of discrete sampling. Like you can't backprop through a discrete sampling. All right, so let's comment that out. All right, so we are calculating the m.logprob action and storing that into action log probs. I guess we may as well just, well, I guess it's fine like that. All right, so then at the end of the episode, we get a reward, and here is the reward. So let's, is this. And I want to normalize it, because this is going to be like between like -1 and 100. I kind of think it would be good to normalize it to be like between like at least no greater than 100. So let's divide it by 100. Let's do it like this because sometimes it doesn't like doing like in place things. Like because with dot torch and gradient, sometimes that doesn't work well. So I'm just going to explicitly do it like this. All right, so we got our episode reward, and oh, actually, the reward for the episode is going to be it can be greater than one actually. But generally it won't be. It'll be between like so if I didn't divide it by 100, I think it's going to be between like minus 200 and 100 or something like that. Like if we kill the alien straight away, we get plus 100. If we never kill the alien, I think we get like a minus 200 because there's 200 time steps. I think the number of time steps is set in one of these options up here. Like set episode timeout to 200. So the worst case, it's going to get like -1 for 200 steps. It's minus 200. So if we divide it by 100, it's not perfectly normalizing it into like -1 or something like that. But it's not terrible. All right. So now we're going to calculate our loss. So let's calculate the losses per time step. So that is going to be and we're going to multiply the reward, right? And I think this should be negative. So here we're going to do minus log prob times episode reward. And then take the sum. So let's do losses t equal torch dot stack maybe. Let's print out how that looks. And then abandon. All right, so we get a tensor and it has a grad FN, so this is going to work with backprop, etc. Yeah, and then we can just take the sum of that. So loss equal this dot sum, and then we can print the loss, and hopefully that looks okay. So all of this is taking forever, and also like let's turn off the window because that's so slow. All right, so here's our loss, and it's got a gradient. Yeah, let's turn off the display of this. Let's comment that out. All right, so here's our reward minus 255. Here's our loss minus 560, and then we can backprop through that. All right, so let's end this video here. So what have we done here? We have added in the sampling from the categorical distribution, and we have thought about how we're going to give the reward. Like, are we going to give it per step and per episode? And we decided, you know what? Let's give it per episode so that we reward. So that we reward all of the actions along the way, not just like the fire button. Otherwise, it's just a fire all the time. And then what we decided is that this we can calculate each time step and just store the result. And then at the end of the episode, we're going to take each of these, multiply by the reward, sum them all up, and that's the loss. And that's where we got to now. So we have the loss. So now we've got the loss, we can then backprop, but we'll do that in the next video. So see you there.